Okay, this is a spreadsheet of the Backwater curves lab data. This is data that I collected and I'm just going to go through the data now and show you what you need to do with this data and how to interpret it. Okay, right. Channel width measurements. The channel width is nominally 60 centimeters, but on measuring it in 6 different places, it was a little bit less. This is the width in meters, so you need to work out a mean width. The flow was measured at 2 times during the experiment. It was measured on the device as in meters cubed per hours. So, and they were very close. There was very little variation. There's a relatively new pump on it, and it's very smooth now. So you need to convert that into meters cubed per hour. Meters cubed per second, and get a mean. Q mean. Okay, and we'll have a B mean as well. The main profile data in the channel to get the slope. Now read the lab handout, but you will see that to get the slope, we let me draw a channel. We have a channel, and we filled it with water up to a certain level. Well, there's a gate. We raised the gate at the end, and we filled it with water to a certain level, and then along the channel at certain points, starting from 0 meters down to 16 meters, actually along the horizontal, we measured 16 points of depth, and we did this 3 times. So the depths at these 16 points, actually 17 points, 0 to 17, 0 to 16, and we measured it 1, 2, 3 times. So there's 3 sets of data, and these have been plotted on this chart here. There's also a trend line which gives you the slope of the channel, slope of that line. Because that slope of these depth measurements that we took give you the slope of the channel. There's a function in Excel. Let me just highlight that function called slope. I'll just click on that to see what that function does. That works out the slope of this data and this X data. It essentially fits a line through the data. So it's a useful function. You could work out the slope by hand, but actually this is much better to use a function in Excel. So it comes out to be about 0.008, slightly higher on 2 other of the readings. So you need to write in here the mean value. That's not mean. Okay. So that's the raw data for the channel before it's flowing. Then undertook some measurements during the actual experiment, and I plotted a bit more of the data for you here. Again, we measured data along the channel at 17 points. Let me just draw the channel again. Remember, the channel's got a sloping channel. We've got a weir at one end, and the profile. There's a jump here, and then there's a rather poor line here. Draw this again. Right, there's a weir at the upstream end. Sorry, a sluice at the upstream end, which forces the flow to go low. Okay, and we measured the data at 0 is just down here, and 16 is the last point. at 17 points along the channel, and those are these data. And we measured the depth at each point 3 times, and these are data 1, data set 2, data set 3. And you'll see on the plot here that they are in fact quite close, which is very nice to know. When we're going to do any comparison of the data and with the integration, we should use a set of mean data. So you're going to have to calculate a mean, and I've also got in the Excel sheet a mean for this supercritical part and a mean for this subcritical part, and you decide whether you need to do what you need to do with that. Part of the lab involves a write-up, so you've got to use this data to do your write-up. You then need to do some calculations. Now it explains in the lab that you need to do a YN calculation, and in this spreadsheet the yellow cells are what you need to calculate. The orange cells, they've got a calculation in there, and you need to do some it will display a calculation at some point. So on this sheet is handily put the a link to the critical depth and normal depth calculations. I'll just rub off those two, right? Because what that does, once you've calculated those, it will draw 2 lines, your critical and YC. So they actually be YN and YC on this channel. Okay, on this diagram for you. So understand that data before you can move on. The YN and YC calculations are actually further down here. The normal depth calculations, you need to do an iteration in here. Now I have given you previously an Excel sheet and recorded a video on how to do an iteration within Excel. Go and have a look at that, and once you've calculated your normal depth, put your normal depth in here. Remember, you're going to have to do this for the Chesney. You're going to have to do it for Manning's. Now for Manning's, this is all set up for you, but you have to choose an appropriate depth. Okay, so you need to set that to yourself, and you choose that as part of the calculation. Actually, this calculation is based on the YN, and this calculation is this one down here is based on the upstream depth. You investigate that, and this calculation is based on the downstream depth. Now, which depth do you use for the Manning's calculation? Well, I'll leave that up to you, and then up to you to justify why you're doing that. The Chesney calculation, there is only one calculation. So if you don't realise that the Manning's are actually a function of depth, so you need to choose appropriate depth. There's also a calculation for the critical depth. Now you have to put the critical depth calculation in here and base that on the flow rate. Here's the formula. So there's a flow rate and the width, the breadth, BC, in here. Okay, so calculations that are half done for you. Then you go back to once you've got those Manning's ends in here, it will draw the critical depth and normal depth. It will draw them on this. You then need to actually do an integration. I've got some graphs set up. I'll explain further what the graph should look like in the lab screencast, but these tables are all pretty much set up for you to go and do that calculation. understand these tables, and once you've got data in these tables, it can appear on these charts. You can do your own spreadsheet. That's fine, but I've set things up for you to do it here. So that's an integration with the Chessie C, and then there's a similar integration with the Manning's N that you use. I've handily put all the relevant equations here. So actually, to get all of the plots you need to have on this diagram, you need to complete this table for the integration from the upstream end. And you need to calculate the sequent depth, which comes from so this sequent depth calculation is one of these. That one is on the calculation for the downstream end integration, the subcritical integration. I'll sketch on this picture, on this graph, what diagram it is you are trying to get. Now, let's draw a water surface. You're going to integrate. You're going to start an integration at this end, and you're going to go there. And there's your surface. You're going to start another integration from the other end, and you're going to go up to there. Okay. You can calculate what we call a sequent depth from one of these two equations, and sequent line I'm going to draw as a dashed line. Okay, for that's the sequent depth to sequent or conjugate depth. Both the same, different words for the same thing. And from the upstream end, the conjugate depth will be up there. So what it is the equivalent, a line with equivalent energy. So that flow at this height has got the same energy as the flow at that height. And where these all cross, the line, you would expect a hydraulic jump to happen. Now these two points might not be in exactly the same place, and that'll be a numerical or a measurement issue, and you need to decide that, think about that, and then discuss it in part of your results. You might want to also on this chart sketch the actual measured data. So the measured data might be something like this. It won't be a vertical line, but it might be similar. It might be in a similar place. It might be in a very different place. I'll leave that for you to calculate. Okay.